Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi everybody. Guys, how are you today? Today topic is about air standard cycle. Okay, and we are in the chapter number 5. So first of all, I would like to make an acknowledgement to my friends in UITM Shahlam for their efforts of prepared this slide. Thank you very much to Dr. Idris Saad, Dr. Al Hassan Salami, and also Dr. Noor Afifah Yahaya. Part 3 for air standard cycle. Today class, we will discuss on the diesel cycle, the ideal cycle for compression ignition engines. For your information, this topic, the outcomes for the students, you should able to uh, solve the problems that based on the diesel cycle. Introductions to diesel cycle. The diesel engines, or correctly known as a compressions, ignitions, or CI engines. Okay, it is a internal combustion engine (IC) engines in which emissions of fuel that has been injected into the combustion chamber is caused by the high temperature which gas achieve. Okay, and either the air when greatly compressed. Okay, at the adiabatic compressions. So the diesel engines has been proposed by Rudolf Diesel in 1892, which would require much higher compressor than is needed for compression ignitions. So this idea was to compress the air, okay, so tightly that the temperature of the air would exceed that of combustions. This engine have highest thermal efficiency. Uh, that means engine efficiency of any practical internal or external combustion engines due to its very high expansion ratio and inherent lean burn, which enables heat dissipations by the exit air. So normally, these engines have used for heavy duty, okay, transportations due to high torque produced by the engine. So for CI engines, it also have a four-stroke engines. Basically, the difference between diesel engines and gasoline engines is that diesel engines, the fuel, okay, the fuel is sprayed into the combustion chamber through fuel injector nozzle. Okay, just when the air in each chamber has placed under such great pressure that it's not enough to init the flow spontaneously. So actually, when we want to make the comparison between the gasolines and diesel engines, what is one of the factor that different is in the diesel engine, it have a fuel injector that is placed at the spark plug uh, of the gasoline or petrol engines. Okay, as you see in these pictures at the right, so this is a view uh, what I'm talking about. Okay, so at the left side, okay, this is the processes or what happened in the cross sections of the diesel engines. Okay, for four-stroke engines, as we learned in petrol engines, it have four processes. Okay, in the uh, same as in the CI engine or diesel engines. For four strokes, is also uh, same as the petrol engines. Okay, this is what I talking about the four-stroke engines. Stroke number one is the intake engines, where the at the left side, where the air has been inducted into the combustion chamber. Okay, and at these situations, the intake valve is opened. Then at stroke number two, that's mean at compression stroke, the intake valve close and also the exhaust valve close, and the piston in the cylinder will compress the air until it come to the power stroke. Okay, process number three or stroke number three. So at these situations, what happened? The fuel being injected into the combustion chamber, and what happened? The fuel and the hot air from the compressed air will burn itself, and then push the piston downward with a powerful combustor. Okay, combustions. So the piston will go down and then rotate the crankshaft. Okay, rotating along through the conducting rod. Okay, and then lastly for the stroke number four, uh, the exhaust valve will be opened, and then all the mixture or combustions mixture will push or will be pushed out to the environment uh, within the exhaust through the exhaust valve and also to the exhaust. Okay, that is the how the process of the four-stroke diesel engines. Okay, for the thermodynamics, we want to uh, discuss or learn about the analysis and the calculations based on the compressions injection engine and the cycles that compatible for these compressions injection engines or diesel engines is called as a diesel cycle. At the left side is the actual process happened, okay, in the diesel cycles when we draw or when we get the result from the engine indicator diagram. Okay, but when you want to make the analysis and also to calculate some of the efficiency of this engine, we have to make or we have to consider uh, some of the assumptions. Okay, so to do so, you So you have to assume, or you have to make the cycle as an ideal cycle. Okay, ideal diesel cycle, as shown in the right side of this slide. Okay, as you see in the pressure versus specific volume, there are four processes. Okay, process number one is isentropic process or adiabatic process. That means state number one to state number two. State number two to state number three is a constant pressure process. Okay. Uh, state num or uh, state number okay, state number three to state number four is again isentropic process, and state number four to state number one is a constant volume process. So to analyze these processes that I have said just now, so some of the related formula can be used as we learned, same as the petrol engines. For isentropic compressions, you can use the formula that can be used in the isentropic process and gas phase. That means three properties related formulas. That means at this left side, okay, this one, properties of ratio of pressure, ratio of volume, and also ratio of temperature. Because of these three properties can be used only in the process of isentropic process. Okay, and at this situation also you can get, or you can calculate the work process 1 and 2, okay, using this formula. Okay, this formula is for isentropic compressions. For process number 2, the related formula that can be used is Q in. That means at these conditions, the heat been applied to the diesel cycles or to the diesel's engines. Okay, so to calculate the Q in for this system, you can use this formula where mCp delta T. Okay, I will explain how to get this formula, and also from the general equations of compression efficiency, or using mass of fuel, and also the calorific value of the fuel, so you can also calculate the Q in. For process number 3, that's mean 3, 4, is again, this is the isentropic expansion. So the formula three properties ratio related can be used, and then also the work that you can find using this formula, pressure, and also have the volume, and also K. K is the ratio of specific heat at constant pressure over specific heat at constant volume. And process number 4 is constant volume heat rejection. At these conditions, the heat out can be calculated using the formula of mCv delta T. Okay, this is the analysis or derivations, how the formula that I mentions in the previous slide. Okay, we can use to calculate the efficiency of the diesel engines. Normally, the thermal efficiency based on the general equations is W, okay, W net over Q in. Okay, so W net is Q in minus Q out. So Q in, so we can simplify these equations, then it will give 1 minus Q out over Q in. By applying the first closed system to process 2, 3, okay, at process 2, 3 is constant pressure. So we apply first law, where the first law mentions that Q minus W is equal to delta U. Okay, so to get at these situations, W net is equals to W other sources of work that have in that process plus work that has been done in that process. It is also equals to zero. Zero, that in no other works that have in this process, only work done by the system. So we lastly we get the work that have been done by the system is P delta V. That means V3 minus V2. Okay. Why V3? Because final minus initial. Okay, true for constant specific heat. Q net, that means Q net 2, 3 is Q in actually. Okay, is equals to delta U plus W, where P2 times delta V is W, and we have determined W, okay, from these equations, and from these equations, Q in can be simplified and become Q in is equals to MCP delta T. Okay, how I get this MCP delta T? Okay, based on the second equation here, MCV delta T plus MR delta T. Okay, uh, simplify the equations. You get out, you take out MCV. Okay, MCV uh, plus R. Okay, actually, uh, as you learn in chapter number 2 in either gas subchapter, there was the equations know the relationship between specific heat at constant pressure and also constant volume. So Cp minus Cv is equals to R. So from there, that's why Cv and C and R is in term of Cp. Okay, Cp is equals to R plus Cv. Okay, so that's why it's come like that, like this. Okay, the equations. Okay, this is for Q in. Okay, Q in. How you want to find Q in process number 2. Then for process number 4, that's mean at process state 4 to 1, you see in this diagrams, for one's volume is constant. Okay, for volume also again, for volume is constant. Again, apply the first law of closed system, because at this situation we assume that the system is closed perfectly, completely. So Q minus W is equal to delta U for process 4, 1. And we want to find W. At these situations, W is 0. Why? Because it is constant volume. Constant volume, W is 0. Okay. So work net for 4, 1 is 0. And this question only will be as Q net for 1 is equals to delta for U for 1. Okay. So again, remember perfect gas subchapter, where the formula of U internal energy is mCv delta T. So you put these equations form this formula to these equations, then you will get Q out is equals to mCv delta T. And the thermal efficiency will becomes 1 minus Q out over Q in. Okay, substituting all Q out and Q in into these equations, and then you will get the thermal efficiency as appear at this slide. Okay, this is the thermal efficiency. Okay, we continue. You know, okay, this is the diesel cycles, and it use air. So because it is air, it is a gas phase. So for the gas phase, the applications calculations can be done based on the perfect gas. Okay, that is the assumptions that you have to do. So by the perfect gas, you know the perfect gas of equation of the perfect gas, PV equal to MRT. MR is constant, so you will get for state 1 and state 4, 1 and 4. Okay, at this process, PV over T is equal to PV over T for state 1 and state 4. So where from here we know that V4 is equals to V1. So terminate V1 and V4, and you will get T4 over T1 is equal to P4 over P1. Okay, and in the diesel cycles, a new quantity will be introduced to you. The quantity is named as the cut-off ratio. That means cut-off ratio is volume 3 or specific volume 3 over specific volume 2. What is a cut-off ratio? Cut-off ratio actually is the ratio of volume after the combustions divided by volume before combustion occur. Okay, that is a cut-off ratio. So we recall again processes 1 and process 1 and process number 3, 4. Okay, there are isentropic processes, these two process. So the formula that you can use or you can apply in these processes, P1 V1K equal to P2 V2K, also P4 V4 powered by K is equal to P3 V4 V3 powered by K. Okay, this come from the three ratio properties that I have mentioned before. Okay, this one. Okay, this one. All right. Okay, since we know that volume number 4 at state number 4 and state number 1 is equal, and pressure at state number 3 and state number 2 also equal. So we divided these second equations by the first equations, and then from there we will obtain P4 over T4 is equals to ratio V3 over V2 powered by K, where V3 over V2 is cut-off ratio. Okay, and then therefore for the diesel cycles, we can simplify from above determinations. Okay, uh, we put in substituting into the diesel's general equations, T4, T1, T3. So it lastly it will become like this at the blue box here. Okay, This is a diesel cycle that has been finalized. Favorite questions. We want you to derive, okay, uh, to get the final equation of diesel's thermal efficiency. I will show you the derivations, how to get the diesel thermal efficiency. Okay. Okay. Firstly, uh, we draw or sketch the PV diagram of diesel cycle. State number 1, number 2, number 3, number 4. This is Q in, Q out. Okay, as you all know, the thermal efficiency of diesel is equals to work done over heat supply. And the formula is 1 minus CV over CP T4 minus T1 over T3 over T2. We simplify this formula over K 4 over T1 T3 T2. Okay, then this is the general equations. Okay, from here we know that the compression ratio V1 over V2, cut-off ratio V3 over V2, expansion ratio V4 over V3. Okay, V4 over V3 also can be write as V1 over V3 is equal V1 over V3. And we can also write as V1 over V2 prime V2 over V3, and this is a compression ratio, and this one is inverse of cut-off ratio, 1 per RC. Okay. Okay. To derive this thermal efficiency of diesels, uh, to uh, show the last equations in term of K and also sign of RC, we can start with uh, we can start with process, yeah, 1, 2. 1, 2, that is adiabatic compression. T2 over T1 is equals V2, sorry, V1 over V2, okay, K minus 1. And from here, T2 is equals to T1 V1 over V2 K minus 1 is equals to T1 R K minus 1. Okay, this is equation number 2. Okay, R is a compression ratio. And then from fuel cut off ratio, RC is equal to V3 over V2. And it is also equal to T3 over T2, where this come from PV M is constant, PV per T 3 is equals to PV per T 2. So at this process 1, 2, 3, okay, process 2, 3, this process 2, 3 is constant pressure. So V3 over V2 is equal to V3 over T3 over T2. Okay. So we rearrange T3 is equals to uh, RC T2. V3 over V2 is RC ratio. Is also can be equals to RC T1 R K minus 1. Okay, this is equation number 3 in terms of temperature 3. Now we look on process 3.1. There is adiabatic expansion. Okay, adiabatic expansions can use um, isentropic relationship ratio T3 T4 is equal V4 over V3 K minus 1. Okay, so T4, T3, V4 over V3, K minus 1. Okay. So is equals to T3 R over RC K minus 1. Okay, where V4 or V3 is expansion ratio. So V4 over V3 is expansion ratio. So expansion ratio okay, this is expansion ratio. So when we combine this is R over RC. Okay, this one is R over RC. Okay, V4 over V3. Okay, that's why R over IC we put in here, and T3 T3 is T1 times RC R K minus 1 over R K minus 1 times RC K minus 1. Okay, so we can minute this, and lastly it will become T4 is equal to T1 RC K. Then is question number 4. Then so we substitute okay, substitute T2, T3, T4. That means from equations 2, 3, and 4 into and dissolves equals to 1 point K T4 minus T1 over T3 T2. Okay, we put all together into this equation, these are equations. Then it will become as 1 minus 1 over K T1 RCK minus T1 over T1 RC R K minus 1 T1 R K minus 1. Okay, close bracket. Okay, it will be like this, and then we simplify this equation. 1 per K T1 RC K minus 1 over T1 RC K minus 1 minus K minus 1. One minus 1 over K R K minus 1 close bracket RC K minus 1 over RC minus 1. Then lastly we rearrange this formula is equals to 1 minus 1 over R K minus 1 K RC K minus 1 to RC minus 1. This is N result. Okay, so this is how you derive the thermal efficiency of diesels from the basics general formula from W net over heat supply until you get the N simplified formula for diesels as shown in the slide. Hope you understand this derivation. Okay, to understand more about these diesel cycles, let's look on the sample problems. Okay, 5.2. So here the problems ask you an air standard cycle, diesel cycle, has a compression ratio of 18 and a cut-off ratio of 2.5. The state of the beginning of compressions is fed by pressure equals to 0.9 bar and temperature 300 Kelvin. Calculate number 1 the thermal efficiency of the cycle, number 2 the maximum pressure, and number 3 the main effective pressure. Okay, to solve or to analyze these questions, firstly you have to draw the or sketch the PV diagram. Okay, so you also have to remember for diesel cycles, the process number 2 is constant pressure. So you have to draw 4 processes, 2 isentropic processes. This is as an ideal diesel cycles. And then process number 2, constant pressure, where at this process Q in is equal. And process number 4 is constant volume, where at these conditions Q out is obtained. Okay. So then list down the data that has been given. In this case, the compression ratio V1 over V2 is 18, and the cut-off ratio, you know the cut-off ratio, V3 over V2 is 2.4, 2.5. So also list the pressure P1, 0.9 times 10 powered by 5 Pascal, and T1 is 300 kelvins. Okay, that is data that have been given to you. Then we start with the process 1, 2. This is the process of isentropic compressions. What happened at this process? You can use uh, this isentropic formula. Okay, uh, ratio of temperature is equals to ratio of volume powered by K minus 1. Why I use volume, not pressure? Because at this pressure we only know the volume. Okay, so when you want to find temperature, T2 is equals to 953.3 kelvins. Okay, and then process number 2 as constant pressure heat addition. uh, at this uh, process, use the relationship of ideal gas PV MRT. Okay, so you ignore or terminate all the constant value, then you will get V2 over T2 is equal to V3 over T3. Okay, you will get this. Okay, you will get this. So this to find temperature. Okay, to find temperature, the formula that we will use to find the temperature 3, the formula that will be used is based on the uh, ideal gas approach. So this one T3 over T2 is equals to T3 over V2. This is come from PVMRT. Okay, and then the knowledge that you know at these situations, P2 is equal to P3. So simplify, then you will get T3 is 2383.3 Kelvin. And process 3-4 is isentropic process. So for isentropic process, V4, you will use the isentropic formula. Okay, but here some of the tricky or creativity of yourself you have to apply here, where what I mean is, okay, you get here V4 over V3. Actually, V4 over V3 is equals to V1 over V2 times V2 over V3. Okay, because in this question, it give the value in term of ratio. Okay, so compression ratio. So you have to find V4 and V3. That's mean from here, what happened? You creativity come out the formula like this, because V2 can be neglect. Okay, so we have V1 over V3, but you know that V4 is equals to V1. Okay, V4 is equal to V1. That's why we can use the compression ratio time the cut-off ratio. But this is the inverse of the cut-off ratio. So when we put all the value in this formula, it will give you 7.2. Okay, 7.2 of ratio. So substituting this value into the isentropic formula, then you will get T4 is equals to 1082 Kelvin. Now we will find Q in, Q out, and W net, because in the formula of thermal efficiency of diesel engine, all this value is needed. Okay, so Q in using the formula NCP delta T. So substituting all the temperature and CP that has been determined earlier. So we will get Q in, Q out, and also lastly W net. So these all values putting in the thermal efficiency of diesel engine formula, then it will give you 60.93% for thermal efficiency. Then P maximum, you know that from the theoreticals and also from the knowledge of thermodynamics here at process number 2 is equals P2 is equal to P3, okay, P maximum. So find P2, okay, using this formula. Then you will get the P2 is equals to 5148 kilopascal. Why using this formula? Because P at process number 2 is process constant pressure. So using the PVMRT equations, okay, and neglect what is not important there, then you get these equations, and then you will get the answer. For MEP, okay, mean effective pressure, using the formula W net per volume times 1 minus 1 over R, where I get this formula MEP. Okay, remember in last slide, in last chapter, sorry, in air standard cycle part 2 or part 1, I have explained what is MEP and what the formula for MEP. So using this formula and then putting all the values in the formula, and then we will get 696.1 kilopascal. Okay. Okay, this is a quite easy questions and solutions. So this is how you will understand uh, the calculation or analysis that you must know. Okay, this is another example, but I think this example you can try to answer yourself as a training. Okay, you try to train yourself to solve the diesel's cycles analysis. Okay, that's all for today lecture. So I think this is for part 3. Uh, so we have complete air standard cycles for chapter number 5. Okay, thank you very much for your listening, for your listening this lecture. Please review, okay, uh, every time if you don't understand, okay, this analysis of diesel cycles. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.